Okay, atomic mass, relative or absolute? We're going to talk here about atomic mass and how it was defined originally in terms of the mole and the molar mass of substances and how that was all defined relatively. So we're going to focus on a lot of where the stuff comes from and their definitions at first. And then at the end, we're going to practice a skill where we can come up with the molar mass of a compound. So the mole was used as a standard amount of a substance. Again, like I said, back when they came up with all this stuff, they didn't even know how big a proton or a neutron was. In fact, they didn't even know that they existed. And so the mole was a standard amount, but they didn't know how many atoms were in a mole. They just used it to compare things relative to one another. They had a nice controllable substance, carbon-12. So they set all things relative to that. Carbon-12 then was defined that 12 grams of it was how many atoms there were. Now you might be thinking carbon-12, so of course they used 12 grams. But you have to remember they didn't know what protons and neutrons were, so they didn't know it was carbon-12. They just knew it was carbon. So they made carbon 12 grams. Why would they have chosen 12 grams for carbon? Well, remember, they had a whole bunch of different elements already figured out. And they knew that hydrogen was the smallest element that they kept finding. So they knew the ratio between hydrogen and carbon was 1 to 12. They didn't want to use hydrogen because it wasn't as easy of a substance to work with, so they started with carbon. But they didn't. If they had set carbon to 1, then hydrogen would have ended up being 0.0833. And that is just an annoying number to work with. So setting carbon to 1, even though it was a standard, was a bad choice. Instead, they said, since it's 12 times bigger than that, let's set that to 12 grams. And then that one will work out to be 1 gram. And that's a much easier to work with number. So really, the choice to set carbon to 12 grams was related to its ratio to hydrogen to make sure that hydrogen worked out to 1 gram. So they said, fine, from now on, 12 grams of carbon represents the mass of 1 mole of carbon. And that's how big a mole is. So that's how they set up that definition. Atomic mass versus molar mass then. So when we look at that 12 on the periodic table, when we say carbon 12, that can represent the mass of 1 mole if it's in grams, or it can represent the mass of 1 atom. And if that's the case, then we say that 12 is in relative atomic mass units. Relative atomic mass units work out to be 1 U is equal to 1.66 times 10 to the negative 24 grams. They were able to figure that out later when they figured out the size of a proton. In fact, that is the mass of a proton or neutron. So since carbon 12 is made up of 6 protons and 6 neutrons, and that's the mass of 1, then we can say 12 times the mass of a proton or a neutron, which we're going to call U, is equal to the mass of 1 carbon atom. So if we wanted the molar mass, it's 12 grams. If we want the atomic mass, it's 12U. What does that actually work out to be? Well, 12U is equal to 12 times 1.66 times 10 to the negative 24. And that is 1.992 times 10 to the negative 23. So 1 carbon atom has a mass of 1.992 times 10 to the negative 23. Since we figured out that mass, so we can figure out the mass of 1 carbon atom, all of a sudden we can figure out how many atoms there are in a mole of something. So I defined 1 mole of carbon to be 12 grams. If I know how many 1 carbon atom has a mass of 1.992 times 10 to the negative 23 grams, this is grams, or this is grams per mole. and this is grams per atom, then I can figure out how many atoms per mole there are. 12 divided by that answer gives us 6.02 times 10 to the 23 atoms. So what they really did historically is they said, we don't really know what this carbon is. It's 12 times bigger than this thing, so let's make 12 grams 1 mole. Then later, when we learned more about the existence of protons and neutrons, we realized that one proton had this mass. We could use that to come up with the mass of a carbon atom, and then all of a sudden we knew 12 grams per mole for the mole definition, and 1.992 times 10 to the negative 23 is the mass of one atom. So the total mass divided by the mass of each individual item tells you the total number of items or particles that you have in a mole. So that's really where Avogadro's number came from. This is true for all other atoms as well. For example, if you look on the periodic table, you'll see that helium has an atomic mass of 4. That means if you wanted the mass of the helium atom, we would say it's 4U. If we wanted the mass of a mole of helium, we'd say it's 4 grams. We use the same number, just different units, keeping in mind that the U represents the mass of an individual proton or neutron. So when we say 4U, we're saying 4 protons and neutrons. So 4 times that mass gives us the mass of the atom. And 4 grams, that's the definition of how big a mole would be for that substance. What's useful then is that we can come up with the molar mass of compounds, and we can figure out how many moles of any compound we have. The way we're going to do that is we're simply going to add the molar mass of the individual atoms that make it up. I realize I'm looking at my examples here and thinking I want to do a really simple one first and then go through these examples to see how to use this a little bit more clearly. So let's imagine a very, very simple compound. Just make myself some space here. Let's imagine a simple compound, diatomic oxygen. If I look on the periodic table, I'm going to see that the atomic mass for oxygen is 16U, or the molar mass is 16 grams, depending on which one we're thinking about. Since we're interested in moles right here, we're going to use this guy, the molar mass. So what would the molar mass of the molecule O2 be? Usually the symbol we use for molar mass, by the way, is a capital M. So what would the molar mass of O2 be? Well, in O2, there are 2 oxygen atoms. If each oxygen atom has a molar mass of 16 grams, then 2 times 16 grams says that there would be 32 grams in a mole of O2. So what we're doing here is the molar mass of the compound, O2, is equal to the addition of the molar mass of the atoms that make it up. Here we have 2 oxygen atoms. So we want 2 times the molar mass of oxygen, which is 2 times 16. If we have a compound like CH4, then, and we want to know the molar mass of that compound, we can take the molar mass of carbon plus the molar mass of 4 hydrogens. So the molar mass of CH4 would be equal to the molar mass of carbon plus 4 times the molar mass of hydrogen. 4 times, because there are 4 hydrogen atoms. This is basically 12 grams per mole. I'm doing some rounding here. The values in the back of your textbook are a little more accurate, but I like to just use the rounded numbers. It makes it easier. 4 times hydrogen is 1 gram per mole. So for that compound, if I wanted a mole of CH4, I would get 12 plus 4 or 16 grams per mole. That's nice and easy in a relatively simple compound. The concept for bigger compounds like these isn't any different. It just gets more annoying the more things you add in. So let's deal with sodium nitrate, NaNO3. What would be the mass of 1 mole of that substance? Well, or the molar mass of NaNO3. I'd have to take the molar mass of Na plus the molar mass of N plus 3 times the molar mass of oxygen, because there's 3. I forget nitrogen, I have to look them up just a second. Not nitrogen, sodium. Sodium works out to 23. Nitrogen, I think, is 14. Yep. And oxygen is 3. I can just get those numbers right out of the periodic table on the back floor. So 23 plus 14 plus 3 times 16 is 85 grams per mole. So if I had a mole of sodium nitrate atoms, the mass of that mole would be 85 grams per mole. One more here, PbNO3, 4, so lead 4 nitrate. And I just do this one so that I remember how to handle this 4 outside the brackets here. So the molar mass of PbNO3, 4 is going to be the molar mass of Pb plus 4 times all of this stuff, the molar mass of nitrogen, plus 3 molar masses of oxygens. See, this is here, and then I have 4 of them, right? I have 4 of them, so I multiplied by another 4. So lead's a big one. What is he? 207.2 grams per mole. Plus 4 times nitrogen, 2 is 14, and in brackets here 3 times 16 for the oxygens. And following your bed mass and being careful, you're going to get 455.2 grams per mole. So sort of lots of different concepts in this video, hopefully all coming together. Number 1, they defined a mole of carbon to be carbon 12, to be 12 grams. That's because they knew it relative to hydrogen, and that allowed them to set hydrogen to 1 gram, which is a convenient number for the smallest thing. Later, they figured out how big a proton was. They figured out that it was 1.66 times 10 to the negative 24 grams. So if they wanted to keep those old numbers like 12 or 16 or whatever, 12 grams, they decided that they could say the molar mass would be 16 grams, and the actual atomic mass would be 16 U, where U worked out to be the size of a proton or a neutron. So 16 protons and neutrons coming together would give you the atomic mass, and 16 grams is defined for a mole. And since often we're dealing with large compounds that combine lots of little atoms, the mole of an entire compound is simply the sum of the molar masses of the objects that make it up. So if we had CH4, 12 plus 4 hydrogens at 1H gets us a molecule with a total mass of 16 grams per mole. I guess we could even say that we could get the mass of an individual methane molecule as 16U if we wanted to use the atomic mass instead of the molar mass for some reason, or the molecular mass instead of the molar mass for some reason. So that's all that.